Hello everyone, my name is Yaxuan, and the work I'm presenting today is on speech audio generation. We are using dynamic MRI image sequences in the vocal area to reconstruct the corresponding audio signal. And the method is based on a conditional variational autoencoder, and we name it KE-CVAE for short. KE stands for the knowledge enhancement, and this work is a collaboration from many institutions, such as the Harvard Medical School and the University of Hong Kong. And real-time dynamic MRI captures the vocal tract shape changes with high construct during pronunciation of speech. This is valuable for speech motor research and clinical applications. However, obtaining clean speech inside the MRI scanner is hard. And you can see the image. Here is a common environment. We capture the MRI voices. And the mic must be MR compatible, and the pulse sequence generates strong background noise. The reconstruction workflow is extremely complex. Therefore, directly recovering speech from a dynamic MRI is a necessary task. Conventional denoising helps, but fully removes scanner noise. Other many-stage processing pipelines were extremely complex and didn't directly handle cine-style dynamic MRI. Therefore, we need an end-to-end approach that handles both MRI and audio domain knowledge well. End-to-end variational inference has shown strong potential for audio generation, yet combining it with domain knowledge from cine MRI to generate audio is not fully explored. That's our motivation. And we show a two-stage pipeline. First is knowledge enhancement, and then follows a conditional variational inference. In stage 1, we pre-train a teacher-student VIT with large-scale high-dynamic MRI in a self-supervised manner. In stage 2, using the MRI sequences as the condition, we learn the latent distribution of audio and generate its waveforms. Here is our model architecture, and you can see in the knowledge enhancement, we input the image to the student network and the teacher network, but the student network input is masked and cropped so that we can ensure the model can learn about can understand the image information, not just memorize it. And in the inference tab, we input the embedding captured by the student network to MRI visual extractor and get the conditional embedding Z, and input it to the decoder and decode the voice. Is the decoder, what the decoder do? And I will introduce our model in detail. In the KE stage, we built our dataset by collecting 13 open high-dynamic MRI datasets, cropping to focus on the vocal tract to obtain a mid-sagittal image. The teacher-student VIT learns speech-related structure representations via global and local consistency, masked reconstruction, and color regularization, helping the downstream model understand oral structures. And in the CVAE stage, the MRI sequence conditions the plural over latent variables. The postural is matched using the target audio. A hi-fi gain decoder generates the waveform. The objective combines reconstruction and KL divergence, plus future matching, and I'm going to skip the math details. We use open speech MRI dataset with 75 subjects, 80 and 20 for training and testing. The backbone includes a 12-layer VIT encoder, a WaveNet post-row encoder, and a Hi-Fi GAN V1 decoder. We pre-trained KE for 40 epochs, then trained the CVAE for 100 epochs, and totally 48 GPU hours on A100. And this is the dataset we collected. And I have to point out that it's open source on the Hugging Face 2 months ago. We use three evolution metrics. The first is Cora 2D for audio correlation, and the second is PESQ for speech quality. And a subjective mode score from 10 people on generated audio clips. Compared with two baselines, our method achieved consistent, higher performance on all three metrics. And I have to point out that because to our best knowledge, we are the first method to solve this problem, so we don't have much method to compare with. So I have to find two baselines, which is based on the Xing and the transformer. And here are some visual results. Audio waveform shows that our method meets better with the ground truth. Notice that dropping knowledge enhancement or using a transformer both yields worse results. And here are some generated audio compared to the truth, but I don't know how to play it. So if you are interested in it, you can come to the next day poster and I will show you. It's very similar to the ground truth. We still have work to do, such as long speech, broader protocols, cross-platform data, and so on. In conclusion, we talked about a clean two-stage pipeline, self-supervised knowledge enhancement plus MRI conditioned CVAE. It generates speech audio directly from Cine dynamic MRI and addresses challenges in MRI. Thank you for your listening, and I'm happy to take some questions.